In this video, we're going to be to solve a very specific type of differential equation, which leads to an exponential model. So the very first example we did for differential equations was the population of deer, and it was doubling every year, and it gave you this differential equation. The change in population was basically 2 times the current population, because that would cause it to double. And this is a very common differential equation in general, so it can be generalized like this. Right, the change in y over x is just some constant times y. All right, so that's the kind of differential equation. We're going to be talking about this very simple differential equation, and it comes out with a very nice solution as well. All right, so can we actually find a solution? We're not given the solution like we were in our previous video where we were verifying solutions. Can we find a solution? This isn't something we know how to do yet. All right, we'll kind of learn this in a future lesson. All right, but for right now, I'll kind of show you how to do it. So what I'm going to do is get the y's together on one side and get the x's on the other side. So I'm going to divide both sides by y, because I want to move this over here. I'm going to multiply both sides by dx, because I want to get the x's to the other side. So here, those cancel, those cancel. So now my equation is going to be dy over y equals k dx. And now that I have kind of the y's on one side and the x's on the other, I can take the integral of both sides. On the left-hand side, I'm taking the integral of 1 over y. All right, this is one of our special integrals. This turns into the natural log of y. All right, so that's just one of our antiderivatives. The antiderivative of k is just a constant. So if this was like the integral of 2, that turns into 2x. So this is going to turn into kx. We can't forget when we do these, we do a plus c. Technically, you have a plus c on both sides, but you can just move it over to just be a single c on the right-hand side. All right, now I want to solve for y, so I'm going to raise both sides to the e. All right, why do I do that? Because e and natural log are opposites. They're inverses, so they cancel. I get this expression. And that's technically the answer, but we'll write it in a little bit nicer form. So the first thing I'm going to do is split this up into 2 exponentials. And an exponential to a constant is the same as just some constant, so we'll just write it like this. All right, so this is the solution to these types of differential equations. When we know it's directly proportional to y, our solution is going to be y equals c e to the kx. So c and k are both constants that we don't know at the beginning, and that's kind of part of the process, is figuring out what k and c are. All right, so the first example, again, a long kind of extra amount of information in the problem. The AP test is always going to do this, kind of slightly confuse you or to try to make it related to real world stuff. But when you break it down, you'll see it's modeled by the differential equation. It looks like this. This is just like our basic model when it's directly proportional to a. Which of the following could be the expression for a of t? So which of these could be the solution for a? And basically there's only one that looks like what we came up with on the last slide. Remember, it was c e to the kt or kx or whatever variable we had, and that's this one. So this one has to be a, because when it's directly proportional like that, you have to get this type of answer. All right, this one, same idea. All right, you can pause the video and read through it. I don't need to read it to you, but we know it's proportional to the number in addition anytime. So that's just as the growth in the number is directly, so growth is directly proportional to the number of bacteria. So just like that, we know the solution to this is ce to the kt. All right, but they're giving us more information, so they want us to figure out what c and k are. All right, so the first thing says that if we have 100, so 2 hours later, so that's when t is 2. We don't know c yet. The population is 160. Oh, I actually went ahead too far, because there's actually more important information. Initially, there are 100 bacteria, so that means when k or t is 0, let's do that over here. Right, so initially when k is 0, well, this whole thing, e to the k0 turns into just e to the 0, this k times 0. E to the 0 is 1, so that tells me that c is 100. All right, so I can replace that now in this equation. Now we just have to remember how to solve this equation for k. So the first thing we're going to do is get rid of that 100. So I'm going to divide both sides by 100. It's going to be 16 over 10 is 8 over 5. And like we saw previously, to get rid of an exponential, or to get rid of a log, we use an exponential. So to get rid of an exponential, we use a log. So get the natural log of both sides. And those cancel out, just give me 2k, and divide by 2, or multiply by 1/2. It's probably easier to write it as multiplication by 1/2. All right, so now our final answer is the population of these bacteria. They use B for the number of bacteria. Is C was 100, and then K was this 1/2 natural log of 8 over 5 times T. All right, so that's kind of the AP style question where you have to know the basic solution, but then you use the other information to figure out what the values of C and K are. All right, here's another one. All right, optimum conditions, the rate of population is proportional to the population at time t. So the population with respect to time is directly proportional to the population. So again, that fits our criteria. And we know the solution to this is that the population equation has to be CE to the KT. All right, at time t equals 0, the population is 300. So that's going to tell me that C is 300. And at 24, the population is 100. So we can use that now, that the population is going to be 100 at time 24. Now we're going to solve this the same way. I divide both sides by 300 first. Then use natural logs to cancel out that exponential. And then divide by 24. And that's our K value. And now the final question is, at what time t is the population 500? So now the problem would be, the population is 500. We know C. We know K. And we're going to figure out what time t is going to do that. But this is solving just like our previous equation. Divide both sides by 300. That gives us 5/3. I'm just going to be lazy and do that. Then I'm going to take natural logs to cancel everything out. Oops, that natural log should go around that. And I have to divide. All this is just representing K. I'm just being lazy and not writing it. So our final answer is natural log of 5/3 divided by K. That is T. All right, so that is the process. So you can see there's a lot of little steps. The big step is just knowing that if you have this type of differential equation, that is your formula for your answer. And just using the information. So initial time tells me C. The next time I can figure out what K is. And then now that I have the equation, I can plug in 500 for the population and figure out T. All right, so here's one for you to try on your own. All right, similar to some of the previous ones. All right, figure out what the differential equation is. For this one, this is very similar to the last example we just did. And your answer should look something like this. All right, so the final answer you can see in the bottom right, but again, they tell you it's proportional. So you have this. So our answer, or our differential equation, looks like CE to the KT. All right, we know it started at 12 moles, so our initial amount is 12. All right, then when I plug in time 4, I get out 4, so that helps me give my K value down here. And to keep me from rewriting this kind of complicated expression, I just leave it as K until my final answer, but I solve it the same way. Now I want to figure out at what time am I going to get 3 moles, so I plug in 3 for my amount, divide by 12, take natural logs, and then I want to figure out time, so I'm going to divide by K, so K is going to go on the bottom there, and then I just rewrite it now to get the actual final answer with all those values that I found. All right, so in class we're going to just practice verifying solutions the most, because that's good practice for doing derivatives, which we haven't done in a while, so good preparation for the AP exam. I will also do some practice modeling with creating differential equations and making exponential models as well.